All right, guys, get out some notes, and I want you to plot. Just draw like a quick XY axis. I want you to do this on paper. I want to use GeoGebra for you to kind of verify some of the things that you're going to do by hand. But I want you to plot those points A, B, and C. We're gonna start investigating in chapter 5 some interesting relationships that exist inside triangles. Okay, we've already seen some with like an exterior angle, two remote interior angles. We've seen the triangle angle sum theorem. We've dealt a little bit with some interesting facts about isosceles triangles. But now I want to, chapter 5 is strictly focusing kind of on just general triangles. These things will happen inside scalene, isosceles, equilateral, obtuse, acute, right? It happens in all types of triangles. And it just develops a series of additional properties that might be useful to us. Okay. Once we wrap this chapter up, we are going to start talking about in chapter 6 polygons, quadrilaterals, that kind of stuff, and then after we get that done, we'll go back to triangles again in chapter 7. But this is strictly, this chapter is about unique relationships with triangles, and the one we talk about today is referred to as mid-segment. So if you're a person that likes to, in their notes, kind of put a section and all that kind of stuff down, 5.1 is mid-segments of triangles. Okay? Mid-segments of triangles. And we're going to find out what a mid-segment is and figure out some unique, interesting properties of those mid-segments, kind of doing this activity. Okay? So we've got those points A, B, and C. The first thing I want you guys to do is to go through, and I want you to find the midpoint of AB, midpoint of segment AB. Okay? Now, I know it's been quite a bit of time since we've last talked about midpoints, chapter 1, but chapter 1 said that the midpoint is an ordered pair, so I'll write it this way. Okay, so capital M, just the way I label the midpoint, I'll identify it or name it, but it's an ordered pair, and I just put these subscripts to remind me that in this equation, there's a lot of x's and y's. I just want to know that that x and that y are representing the midpoint. But if you remember the formula, all it was is the average of your x's. Okay, so you'll have 2 points. You'll have 2 endpoints. You'll add those together and divide by 2. That's what it means for us to say the average of our x values. And then comma, the average of our y values. Okay? It's one of our kind of larger formulas to write, but it's actually one of the easier ones to deal with. All you're doing is adding together and dividing by 2. Okay? So I want to find the midpoint between A and B. Okay? So we find the midpoint between A and B. So I'm going to add these x values together, 6 and 2. Gives you 8, right? Divide by 2 and you get 4, correct? Okay? I'm going to take my y values, add those together, get 6. Divide by 2, I get 3. So I want you to then plot over here 4, 3. And your 4, 3 should be, if you've drawn things to scale, okay, should land on AB, and it should look like it's halfway in between. Okay, that's why I'll put that point in here. Go ahead and call that point D. So there's the midpoint, and you see that it is at 4, 3. Is that okay? Now I want you guys to go and find the midpoint of BC. Okay, find the midpoint of BC. So now we're looking at 2 different points, 6, 2, and 4, negative 4. Add the respective x's, divide by 2. Add the respective y's, divide by 2. And that should give you the midpoint of BC. And I want you to call that midpoint E. So you add 6 and 4, you get 10. Divided by 2 should give you 5. Add 2 and -4 gives you -2. Divide by 2 should give you -1, right? We get a midpoint of 5, -1. Okay. All right, so how many points do you need to create a line or to create a segment? If I were to give you a ruler and say connect this many points to develop a line, you need how many? 2. Okay. D and E define a line for us, right? They create a segment that we can draw in. So I want you to do the same thing, to draw in that segment, D to E. D to E is referred to as a midsegment, okay? And we're going to call it, and I'll put up the definition for you here in a little bit, but we have to call it a midsegment of a triangle. We have to tell it, we have to be descriptive in regards to what shape it's a midsegment for, because we will have midsegments for other shapes, okay? And there will be different properties for those midsegments than what we see here. There's some relationships, though, that exist between DE and other parts of this triangle. And I've got DE highlighted in red, but I've got the third side, AC, highlighted in blue, right? Okay, the side that we really haven't dealt with yet. We didn't find the midpoint of that third side. We could, and we probably will here in a little bit. But there should be some relationships between this red one and this blue one. And that's what I kind of want to have you guys work on and figure out. The first thing I want you to do is I want you to find the slope of DE. Remember, slope is y2 minus y1 over x2 minus x1. Okay? So I want you to find the slope of DE. And then I want you to find the slope of AC. I want you to find the slope of those two segments. All right, so we find the slope of D to E. You should have, what, 3 minus -1 up top and 4 minus 5 on the bottom, right? Those could be flip-flop, but you should get 4 over -1 or -4 over 1, however you did your subtraction, right? Does that make sense? So we should have gotten a slope of -4 for D to E. All right? When you find the slope of A to C, okay, A to C, I'm looking at the difference in y, so I go 4 minus -4, and then divide by the difference of the x's, so 2 minus 4. So it gives me a positive 8 on the top and a -2 on the bottom. If you were subtracting in a different order, you would get a -8 up top and a positive 2 on the bottom. But regardless, what does that slope reduce to? -4. What do you notice about those two slopes between DE and AC? They're the same. So what does that tell you then about line AC or line segment AC and line segment DE in comparison to one another, if their slopes are the same?
They're parallel.
They're parallel. Okay? So what we find out here, and this is going to be one of our key components of the theorem we learned today, is that the midsegment of a triangle is always parallel to the third side. Okay? And the third side being obviously the side that the midsegment is not intersecting. Okay? Is that doable? Okay, so that's one component of midsegments. Now, the next component takes a little bit more work. I want to find, keep this formula up here. I want to find the lengths of the red segment DE and the blue segment AC. So the first thing I want you to do is remember that the distance formula is the change in your x values squared plus the change in your y values squared. Change meaning difference, right? Or subtraction. Okay? So find the length of DE. Okay, so find the length of DE. I'll give you a minute to do this. Find the length of DE. And then we're going to find the length of AC. And we're going to see if there is a relationship between those two values. So finding the length of DE then, remember subtracting those x values and those y values. So I have 4 minus 5 gives me -1. Square that, I get 1. So that's my delta x squared. Plus then, subtract my y. So 3 minus -1 becomes 3 plus 1, which is 4. I'll square that and I get 16. So 16 becomes my delta y squared. So what's 1 plus 16? Which becomes radical 17, right? That makes sense? Okay. So we get radical 17. Now I want to do the same thing for A to C. While doing that for A to C, we're now going to be dealing with that point there and that point there. So we subtract the x's again. 2 minus 4 gives me -2. But I'm going to square that so I get +4. And then we'll subtract the y. So I get 4 minus -4. That becomes 8. Square that and I get 64. And that gives me radical 68. Okay? Now this becomes a situation where it is useful, maybe one of the first times we recognize the usage of being able to simplify radicals. Because if I look at radical 17 and radical 68, you might look at those and say there's really no connection between the two. There's no relationship. Okay? Now 17 is a prime number, so that's not going to simplify any further. But 68 is composite. Okay? And if we think about 68, a couple different ways of doing this. If I take radical 68 divided by 2, it gives me 34, doesn't it? Is 34 composite? We'll divide 34. 2 again, right? It gives me 2 and 17. Well, now we've broken 68 down to radical 2 times radical 2 times radical 17. What's radical 2 times radical 2? It's 2. Okay? Ultimately gives me radical 4, which is perfect square, so it gives me 2. So radical 68 is actually 2 radical 17. Okay? Now I have absolutely no idea what radical 17 is. It's a little bit bigger than 4, because radical 16 would be 4, right? Okay? But it's an ugly number. But regardless of what that number was, let's just let it be x. How does x and 2x compare to one another? Or if I let it be r, how does r and 2r compare to one another? How does radical 17 and 2 radical 17 compare to one another? How's 1x compared to 2x? It's twice as big, or 2x is twice as big, right? Or 1x is half, okay? So that x is this number that I don't really know what it is, okay? It's 4 point something, okay? But now I got 2 of these, right? So isn't this number twice as big as that one? Okay? So it tells us our second relationship, that this red segment, the mid segment, not only is it parallel to the third side, but it is always, 100% of the time, always half the length of the third side. Okay? Now what I like about GeoGebra, it allows us to double check those things, because right now all we've done is shown that this exists for this triangle. Okay? And the idea or the logic is that may just be happenstance for that one triangle. I just drew the one triangle in which that relationship became true. Is it in fact true for regardless of where those 3 points A, B, and C show up? Okay? So, the nice thing about using GeoGebra is I can move things around. I can ask it for slopes and stuff like that. Okay? A couple different ways I can look at the slope concept. We can actually click the slope tool, click the blue line, click the red line, and we see that says slope of -4 and slope of -4, right? So it verifies the math we did, but here's the idea, is I want to be able to move this around, okay? Are those slopes the same? Now, not the same number in regards to being -4 again, but they're compared to one another, are they still the same? So those two lines are still parallel, right? Okay. Still parallel, still, in this case they're -0.94. No matter where I move C, okay, 6.89, -3.29, wherever I move B, okay, B is not affecting those two. We'll talk maybe why at some point, why B is not affecting those two. But no matter where I move these points, I still get a mid-segment that is parallel to the third side. Is that doable? So hopefully, now that's just a handful of the different possible triangles. Hopefully you realize that, even though this is a lot of different triangles, it's just a handful of the possible infinite number of triangles. So this is by no means a proof, but it's providing us maybe insight that this concept, this property is always going to be true. Okay. Let me go back to the original picture. Okay. So the other thing we can do is we can look at distances. Okay. And you see these distances over here, but if we want to click on these points, we can, or these segments, we can put them in there. Now, you might not want to every single time as you move these things around say, okay, are those twice as big or half as big? Are those twice as big or half as big? So what we can do with GeoGebra is we can say, okay, this red line, which they're saying is I, so I'm going to type in I down here, and then divide it by my blue line's length, which they're saying is H. So take I divided by H and hit enter. It should give me those two numbers divided by one another. And when I do that, I get 0.5. Now, as I move A, B, and C around, all those ordered pairs and all those lengths change, right? But what happens to that 0.5? Absolutely nothing, right? So it's telling me that this number here, whatever that I length is, whatever that red segment's length is, divided by the blue segment's length, will always be 0.5 if D and E are always midpoints. Does that make sense? Okay. Now I went, I divided by H, but I could on H divided by I, and that should give me 2, right? So that's saying that the blue segment is 2 times as big as the red one. Alright? Is that doable for everybody? What happens though is that we not only have that mid-segment, but we have a third midpoint over here, but we didn't find. We have that midpoint, F. Okay, now you guys don't have to write this down on your paper, but there's going to be questions where they ask you to find information about FD and BC. Well, again, if I look at the slope of D to F, and I look at the slope of B to C, are they the same? Okay, so they're parallel. And if we ask to find the distance of I is 3.16, the distance of whatever they're calling that segment, G is 6.32. If I divide those, I do get 2 or 1/2, depending on the order of division. And that stays the same, still parallel, still have that factor of 1/2 or 2 between those two segments. Does that make sense, everybody? So there's another mid-segment. And then the third mid-segment that we could actually have, let's clean some stuff up here, would be that. And that's going to be now parallel to AB, and it's going to be half the length of AB. So what happens is that when you find all 3 midpoints, you can actually create a second triangle on the inside by connecting the midpoints. Okay? And what happens is that second triangle is pretty interesting, some of the features that we find out about that second triangle on the inside. We'll talk about them later throughout this chapter and into the chapter or the sections that we talk about similarity. But those 2 triangles are pretty interrelated. Okay, some really interesting features about them. Even the other 3 triangles that are created there are pretty interesting in comparison to that red one. For instance, let's look at If I've got I, J, and K here, so I, J, and K are those values there, right? If I find, let's see here, that distance there, so 4.12, that's the same thing as K, right? That makes sense, everybody? K being this red segment. If I find the distance here to E to C, that's 3.16, which was the same thing as J. And then I find the distance from E to F, which is 2.24, which is obviously the same thing as I, right? We've just shown those values that this red triangle up here, let me color them in. That triangle there, the maroon one, and that triangle, the blue one, are they congruent by side, side, side? Okay. And we find out that the other two white triangles there are also congruent by side, side, side. So we've got 4 triangles up there that end up being congruent by side, 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 just by dealing with these mid segments. Okay. And like I said, when we start talking about similarity, we'll come back to this set of triangles and deal with similarity again. Okay. But the key concept right now is that when we talk about mid segments of triangles, first of all, to be able to identify where they're at and what creates them, okay, it's simply taking 2 midpoints of a triangle, of the segments of the triangle, and connecting them. Okay. It's critical that we call it a mid-segment of a triangle. Kind of alluded to that earlier. We will have mid-segments of trapezoids eventually. Okay. So if I just say, even after we talk about trapezoids, once I just say mid-segment, you don't know the figure that it belongs to. Okay. So I have to have that connection to which shape. So I have to have of a triangle. The features then that exist for a mid-segment is what we learned in that GeoGebra activity, the activity we had at the beginning, is that the distance of the mid-segment is always half the length of the side that it's parallel to. Okay? And it's always going to be parallel to that third side. Okay? Here it says the segment that joins the midpoints of 2 sides of a triangle. I would not write that. I would write the mid-segment, because that's the definition of mid-segment. It's the segment that joins the 2 midpoints of a triangle. Now, every triangle has how many midpoints? Or segment midpoints? It's going to have 3, right? Triangle has 3 segments, so it's going to have 3 midpoints. Therefore, by connecting any grouping of 2 of those midpoints, you'll eventually get every triangle to have 3 mid-segments. You just have to pay attention to, am I dealing with just 1 mid-segment? Am I dealing with 2 of them, or am I dealing with 3 of them? Okay. Sometimes they like to put all 3 in and just ask you questions about 1 of them. Again, trying to create, just like other things in this class, try to create clutter for you in your picture, so you have to sift through things, find out the things that are important to you, the values that are important to you, and work from there. As you work through these, nothing wrong with saying that AB, in this picture up here, AB is twice as big as DE, or that DE is half the size of AB. Okay? You see that the theorem is in regards to DE equaling half of AB. But if I multiply both sides by 2, it gets me 2 DEs equals 1 AB, right? Okay, so it might be useful to decide when it's appropriate to use the 1/2 ratio or the 2/1 ratio. Okay? So just kind of a quick exercise here. If they give me x, z to be 10, okay, so x to z is 10, so that's going to be this segment here. That z is 10. What is n to m? Gotta be 5, right? Okay, m and t are midpoints. If tn is 7, so t to n is 7. So that is a mid-segment, isn't it? So then what is x to y, which is the side of the largest triangle? 14. Okay, double. Okay. So that's where it's appropriate to use the 2/1 ratio instead of the 1/2 ratio. Z to n is 8. This is one that usually tricks people. If z to n is 8, tab real quick. If z to n is 8, what is n to y? N. If that's 8, n's a midpoint, so that has to be 8 as well, right? Because they're asking me what eventually is that distance right there. And the common answer that I get all the time is 4, because they take half of 8, right? But what should they be taking half of? 16, okay? So that distance there is 8. And that should kind of tag along with that idea that we talked about with all 4 of those triangles and those smaller triangles. All 4 of them are congruent to one another. So all of them have to have a side length of 8, and that's what I was showing. Okay? What about x, y is k? Okay? And then this happens a lot. The further you get into geometry and other math courses, you start to learn some features using numerical values, and then they say, okay, let's get rid of numbers. Let's just use arbitrary values like k. If x, y was k, so x to y, that distance right there is k. What would t to n be? Half of k, right? So 1 over 2 times k, or if you want to write it as k over 2 that way, either one of those is fine. But what that does is allows us now to choose any value for k. And once I choose a value for k, I automatically then know tn. Kind of skip that bottom part, let you do that last one on your own there. There's some other examples here as well you can work through. And I'll leave these up to you to work through. We're going to get down to question 7. This one here talks about, and the math that really isn't hard here, but I want to give you an example of where this would be used. Okay? Let's say that you have in this case it says a sinkhole. Last class we talked about in Yellowstone Park. Okay? There are like sulfur springs, right? Okay, and you cannot touch sulfur. Okay, it will sulfuric acid. It will dissolve you. Does that make sense? Okay. So let's say that we've got this sulfur pond of sulfuric acid. We want to measure the span of it, the width of it. Okay. Does it make sense to have somebody like hold a tape measure here and have the other person walk over there on the other side? No. Okay, you're gonna melt, right? Okay. Doesn't make a whole lot of sense to do that. Even if we've got, maybe techniques that allow us to not have to walk across the lake or anything like that, but walk around it, still have to hold our tape measure across that. We don't want our instruments to melt either, right? Okay, so maybe it's not feasible to directly measure length A to B. So that's what I'm trying to figure out here. Kind of zoom in here so you can see this picture a little bit better. All right, we're trying to go from A to B without having to go across maybe that sulfur spring or sinkhole in this case, I guess. So how can we measure how wide this thing is? Well, the first thing we would do is we would come up to the edges of this thing carefully, and we would create markers at A and B. Okay, so we would put flags there, or like stones or something you can remind yourself of where those points are. Okay, you are then going to find a third point of a triangle. Okay, and hopefully you develop that third point. Okay, so that it is far enough away from B and A, so that the mid segment ends up being on dry land. Does that make sense? Okay, we could have. Let's kind of do it this way. Let's go. I think I can do this way. Okay, so let's say that's our lake, right? Okay. I would want to make sure that that's A and B, right? And I don't want to measure the span across this lake because of the hazards that it creates. Well, what we're going to try to do is try to measure the length of this red segment instead. Okay. and use some properties of that red segment to tell us the length of A to B. Well, if I try to measure that red segment, do I still have the hazards of crossing the lake or sinkhole or whatever? So what I want to do is make sure that this point is far enough away to where that red segment is now on dry land. Does that make sense? And I also want to put it in a position to where the blue segment and, let's color this one pink, this pink segment are also both on dry land. Is that okay with everybody? So I want to be able to find those lengths as well. If I did that, obviously this length here is all on dry land, but the blue segment is not. Okay? So I want basically all three of those, the two sides of the larger triangle, to be on dry land, and the mid segment to be on dry land. Okay? Because what's going to happen, go back to this picture here, is that I can now judge this length from B to E. I can determine that length. I can either put my tape measure here and have somebody walk to E, and we're going to measure that length, right? Now the reason I want to measure that length is because I want to find where D should be located. I want to find where that midpoint should go. Okay? Or, if I don't have a tape measure, I could walk that off, okay, and get a rough estimate of that length so I could find D. Is that doable for everybody? So let's say I walk this off from B to E. I find that to be 100 feet. So then I would come back 50 feet and put a marker right here. Does that make sense to everybody? Okay. Now I do the same thing from A to E. Let's say I walk from A to E, and that's 120 feet. So now I'd walk from E 60 feet back towards A, and I would put a marker down, right? Now the hope is that DC, that mid segment, is on dry land, and I can now measure that mid segment. And we've measured that, and it becomes 46 feet. So if that's 46 feet, our theorem about mid segments tells you that BA has to be what? What does the length of B to A have to be?
92.
92. Has to be twice as big, right? Okay. So there we found a definitive measurement, an exact measurement, but we never had to measure the object that we were interested in. Okay. And that's called indirect measurement. Okay. Measuring or finding the length of something without focusing on that object. Okay. Using other things and theorems and properties, other segments, other angles to help us find those measurements. Okay? A big component of mathematics and science is to understand indirect measurement. Measuring something that we know, something that's easily accessible, to find measurements of something else that is not easily accessible or easily known. Okay? You think about everything that we do in regards to like space travel and that kind of stuff. All that is indirect measurement. We've never been to Pluto, right? But we know its circumference. We know its, all the things. Its orbit. We know all that stuff. Okay, we've never really been there physically, but we were able to use indirect measurement to be able to determine all those things. Does that make sense? Okay. A big part of this course, the remaining part of this course, is to use theorems, postulates, definitions to indirectly measure things. Okay, so that's something that we're going to focus on. Just an example here, real quick with finding X, Y, and Z. I'm going to tell you that D and E are all midpoints. Okay. If I want to find D, or if D and E are midpoints, and I want to find X, Y, and Z, what is the relationship that you're going to set up between maybe those two things? They should be what to one another if E is a midpoint? Equal. So it should say 5y minus 10 is equal to 3y plus 10, right? Okay. What should be the relationship between those two things if D is a midpoint? Equal. So I get 2z squared plus 1/2 y is equal to 3z squared minus 2y. Now if I look at that one, okay, there's a couple things going on with that equation that maybe we don't like. One, it's got the power of 2 in it, right? So we should think factoring. But it's also got 2 variables, correct? So that one isn't a really great equation to start with. But does it make sense to solve this one first And now once I know, and I'll let you guys solve that, but you end up getting y to be 10 there. Does that make this one a little bit easier? Now that's minus 20. And this is plus 5, correct? Okay. Just kind of going through and solving this one. Get all my z squareds on one side. So I'll subtract 2z squared from both sides. Gives me this. Now, because of that form, there's no other z's, right? There's no z to the first power. So when you have this, it's just a z squared and constants. You can isolate z squared, and then you can take square root. So that gives me plus or minus 5 for z. The only thing I want you to be cautious of is when you get two answers, you need to always plug them back in to check. And just because of time, I want to give you a little bit of time to work on some homework here in a moment. When you plug z back in here, whether it's 5 or negative 5, you will get 55 for that length and 55 for that length. And those are both okay distances, right? Okay. Now the last one is what, so that stuff, those midpoints, we did that stuff back in chapter 1 and in chapter 2 when we talked about segment addition with midpoints, setting the parts equal to each other. If I look at finding x now, okay, which x is in DE and BC, correct? Right now, those two things are not equal. Where do I need to put a value, either 1/2 or 2, to make these things equal? What could I put here on DE to make this side equal to BC? DE is always what compared to BC? The mid-segment is always what compared to the third side? It's half, okay? So DE is half of this. So does it make sense that 2 DEs is 1 BC? Okay? Or if you want to go off the way that we stated that the mid-segment, in this case DE, is half the third side being BC, you put the 1/2 there. Regardless, it doesn't matter. You're just both routes are going to get you the same answer. If I could do 2 DEs, okay, so that means take 2x plus 16 is then equal to 1 BC, which is 8x minus 12. This gives me 4x plus 32, 8x minus 12. Move your 4x over, move your 12 over. X ends up being 11, right? Okay. Now I look at that and think, I know my relationship. I know there's a 1/2 or a 2 concept, and I know which one should be doubled. Either this should be doubled or this should be, I should take half of that. I would normally take half of this one instead of doubling the other one. Because these two numbers, 8 and negative 12, deal well with a half, don't they? Okay, they're even numbers, so 1/2 is going to be easily multiplied through there. So what I'm going to do is I'm going to take 2x plus 16 is equal to half of 8x minus 12. Well, half of 8x minus 12 means take your half and distribute it through 8x minus 12, so it gives you 4x minus 6. Okay? It provides the same information that line is there going to provide, because everything in this line could have a 2 in it, right? Take a 2 out there, you get 2x. Take a 2 out there, you get 16. Take a 2 out there, you get 4. Take a 2 out there, you get 6. Okay? So if that's the case, then I should be able to solve this and get the same x to be 11. Subtract 2x from both sides, add 6 to both sides, so you get 2x equals 22. X will in fact be 11. Okay? Then you can plug, obviously, built-in checks, plug values back in, plug your 11 back in, see that the segment D to E is 1/2 the segment B to C, and all that. Okay? You should have a Math Excel assignment. Sorry, class went a little bit longer than I anticipated. But it is not something that I don't think is going to take you very long. Last class had a little bit more time than you guys did, and